Good morning, dear students. We will discuss about the subject of microprocessor on the topic of interfacing input-output devices. Myself, Dr. J. Gobinath, Assistant Professor, Department of Physics, Erode Arts and Science College, Erode. Next slide is interfacing input-output devices. Interface act as a communication between user and a computer. It is an integrated circuit which helps in performing basic functions of the CPU. Interfacing is classified into two types: memory interfacing and input-output interfacing. I/O devices data can be transferred between the microprocessor and the outside world. This can be done in groups of 8 bits using the entire data bus. This is called parallel input output. The other method is serial input output, where one bit is transferred at a time using the serial input and serial output pins on the microprocessor. Slide is dealing with input output devices. There are two ways to deal with input output devices. First one is memory mapped input output. Second one is input output mapped. The first one, consider them like any other memory location. They are assigned a 16-bit address within the address range of 8085. The exchange of the data with these devices follows the transfer of data with memory. The user uses the same instructions used for memory. This is called memory mapped input output. Second one is treat them separately from memory. Input output devices are assigned a port number within the 8-bit address range of 00H to FFH. The user in this case would access these devices using the input instruction IN and output instruction OUT separately. This is called input output mapped or peripheral mapped. Then the next slide is basic interfacing concepts. The first step in interfacing an input output device would be to determine which instructions will be used to access it. If you want the user to use the in or out instructions, then it should be interfaced as a peripheral mapped input output device. If the user should use regular data transfer instructions, LDA load accumulator and STA store accumulator, etc., then it should be interfaced as a memory mapped input output device. Next slide is peripheral input output instructions. There are two instructions. The first one is in instruction, second one is out instruction. In instruction, it brings data from an input device to the accumulator. Out instruction, it brings data from the accumulator to an output device. They are both 2-byte instructions, with the second byte holding the 8-bit address of the device. Given that there are separate instructions for input and output, the 8085 can actually communicate with 2 power 8 equal to 256 different input devices and an additionally 256 different output devices. Slide is the execution of the out instruction. The out instruction requires 3 machine cycles and 10 T states. The first cycle is an opcode fetch cycle to fetch the first byte of the instruction from memory. The second cycle is a memory read cycle to bring the 8-bit port number from the next location. The third cycle is an input output write cycle. In this cycle, the 8085 places the port number on AD0 to AD7 and A8 to A15, and the signal WR write is set low. Since the device address is placed on both AD0 to AD7 as well as A8 to A15, there is no need for demultiplexing. AD0 to AD7, A8 to A15 can be directly used to identify the device. The next slide is the execution of the in instruction. The execution of the in instruction is almost identical to that of the out instruction. There are 3 machine cycles and 10 T states. The first machine cycle is the opcode fetch. The second cycle is the memory read to get the port number. The third is an input output read cycle. Again, in T1, the port address 8 bits is placed on both AD0 to AD7 and A8 to A15. The input output bar M signal is set high to indicate an input output operation. At the beginning of T2, the read signal is set low active and the input output device responds by placing the 8-bit data on the data bus. The next slide is the interfacing of output devices. Output devices are usually slow. The output is usually expected to continue appearing on the output device for a long period of time. The data will be present on the data lines for a very short period. It has to be latched externally. The external latch should be enabled when the port address is present on the address bus. The IO bar M signal is high and WR is set low. The resulting signal would be active when the output device is being accessed by the microprocessor. Decoding the address bus for memory mapped devices following the same techniques discussed in interfacing memory. Next slide is the interfacing of input devices. The basic concepts are similar to interfacing of input devices. The address lines are decoded to generate a signal that is active when the particular port is being accessed. An IO-RD signal is generated by combining the IO bar M and the RD signals from the microprocessor. A tri-state buffer is used to connect the input device to the data bus. The control signal is enabled for these buffers is connected to the result of combining the address signal and the signal IORD. The next slide is the examples of interfacing input-output devices. To illustrate the techniques of interfacing input-output devices, the output device is LED. We will design the circuits needed to interface 8 LEDs to display the contents of the accumulator. The next input device is switch as well as 8 switches to set the contents of the accumulator. The diagram shows the LED display with different colors, then different types of toggle switches. The next slide is how to interface the LEDs. Let's first design the external circuit. The data on the data bus from the microprocessor stays for an extremely short amount of time. So in order to keep it long enough for displaying, we will need an external latch. We will use an 8-bit latch to hold the data. We need to connect the 8 LED to the latch's outputs. However, the latch will not be able to source enough current. So we will use the inverted outputs and make it sink the current instead. The diagram shows how to connect 8 LEDs on the breadboard. Next slide, when should the latch be enabled? It needs to be enabled when the data is on the data bus. That happens when the ALE address latch enable signal is low. However, we only want to display the data that is being sent to the input or output. We don't want to display the data being saved in memory. So the latch needs to be enabled only during input or output operations. That happens when IO bar M signal is equal to 1. Finally, we only want to display data intended for our port. We must be decide on a port number, let's say FFH. Now we can design the control circuit on next slide. The next slide is the interfacing of the LEDs, that is control circuit. The latch will be enabled when WR right signal is equal to 0, that is low. Then IO bar M signal is equal to 1, that is high. The address on A8 to A15 is equal to FFH. The A8 to A15 is given to the 8 input AND gate. IO bar M signal is directly given to the output. WR signal is inverted in NOT gate and then give to the output. The totally address lines IO bar M signal and right signal is given to the 3 input AND gate and then latch will be enabled. The next slide is the interfacing of the LEDs with latch. The 8-bit latch is connected within the circuit. The AD0 to AD7 address lines is directly given to the 8-bit latch input side. The other input is latch enabled. The output side, the 8 LEDs and then resistors are connected with the 5 volt power supply. When the latch enabled signal is high, the output is displayed. Other than the latch enabled signal is low, means the output not displayed. Next one is assembly language program for interfacing the LEDs. When a bit on the address bus is 1, the corresponding Q will be 0 and the LED will have 5 volts on the anode and 0 on the cathode. Therefore, LED will be on state. Finally, to write the ALP program, only 3 instructions. First instruction, move immediate a comma has data, that is load the accumulator immediate data to be displayed on LEDs. Second one, out FF, send the accumulator data to output port FF. The last instruction, halt, that is end.